Welcome to another session of thermodynamics. In this session, we're going to learn about the increase of entropy principle. The increase of entropy principle. First, we'll consider a system and a process and a reverse process. Here, the process that from of a system transfers the state 1 of the system to state 2, and it could be any process. Let's say it could be reversible or irreversible. We don't know. We don't know what that is. But to complete the cycle, now the system can be transferred to transfers back to the state 1. Now we're going to use a reversible process to transfer that back into state 1. This is a reversible process. Now, according to the Clausius inequality, according to the Clausius inequality, we can write that for any cycle, the integration of the quantity delta Q over T is less than or equal to 0. Now, in our example, the cycle, there's a cycle that includes two processes. One is state 1 to 2, which is a reversible or irreversible process, which we don't know. And then we have a reversible process which comes from state 2 to 1. And then we can write process 1 to 2 dq over t plus process 2 to 1, that says internal reversible process dq over t, internal reversible, and that according to Clausius inequality should be less than or equal to 0. We also learned that the change of entropy delta S is equal to the change of entropy is equal to 1 to 2, sorry, in this case 2 to 1 delta Q over T if the process is internally reversible. Now our process 2 to 1 is an internal reversible process, so that we can write S1, because that's the final state, S1 minus S2 equal 2 to 1 dq over 2 T internally reversible process. Now, as you can see, we can substitute that into our equation 1 here. We can substitute that into our equation 1, so that we get 1 to 2 delta Q over T plus S1 minus S2 less than or equal to 0. From this we can get S2 minus S1 greater than or equal to 1 over T 1 to 2 delta Q over T. That's an unknown process, that's not an reversible process. Now what we can see is, now initially we know that for an internally reversible process, if the process is internally reversible, the entropy change during the process is equal to this quantity. Actually this quantity integral 1 to 2 delta Q over T represents the entropy transfer due to heat, entropy transfer due to heat. Now, for a not reversible process or irreversible process, we can see that that quantity, the entropy transfer due to heat, is less than the entropy change. So there should be some quantity that needs to be added to supplement the rest of the amount of entropy change takes place in the process 1 to 2, because the entropy at the state 1, that is S1, and the entropy at the state 2 is not going to change as long as the states are the same. So no matter whatever the process that you take to go from 1 to 2 should give us the same entropy change. Either it could be reversible or reversible, because the properties are only depend on the system, state. It does not depend on the process that the system takes to change its state. Therefore, now there could be something going on when an irreversible process takes place in between two states of the same system. That is the entropy generation. So we can say that S2 minus S1 equal to 1 to 2 delta Q over T plus the entropy generation. In a reversible process, this S gen going to be 0. For an irreversible process, S gen is greater than or equal to 0. Sorry, greater than 0. Now, let's consider an isolated system. If you have isolated system, what do you mean by isolated system? Isolated system does not interact with its surroundings. There's no heat or work transfer in between isolated systems and the surroundings. So there's no heat transfer. That means the entropy change S2 minus S1 if an isolated system is equal to S gen. Now entropy generation is a quantity, right? Because we figured out for a reversible process, S gen is for irreversible process, for irreversible process, S gen is greater than 0. So when you take these two into account, we can see that S gen is a quantity that is greater than or equal to 0. Now here what happened is, for an isolated system, S gen is always greater than or equal to 0, or entropy change is also always greater than or equal to 0. Now what we can say is, for an isolated system, entropy of an isolated system during a process always increases, or in the limiting case it will remain constant during a reversible process. So entropy of an isolated system during a process always increases, or in an reversible process remains constant. This is known as the increase of entropy principle. This is known as the increase of entropy principle. Now, if we look into a system, let's say it's an isolated system, that has many subsystems, right? There's an isolated system that's represented by this box, and there are many subsystems inside of it, right? Subsystem 1, sub 1, sub 2, sub 3, okay, subsystems. So since there's no heat transfer in between the isolated system, so this is an isolated system. Between the surrounding and isolated system, we can say the total entropy change. Entropy is an extensive property. It depends on the size of the system. So we have more subsystem. That means we have more size of the system. So the size of the system increases. If we add the entropy change of all the subsystems, where I equals 1 to n delta Si, that will give you the total entropy change, and also that is a positive quantity because that's equal to total entropy generation. Now we can take back this ideology into one system and its surroundings. So let's say you have a system like this, and I can draw a boundary line because I am the one who's going to define. We can define whatever the system that we like. I say that this is my system, and I'm taking a substantial amount of surroundings around it as a second subsystem, and then say this boundary is an isolated system, sufficiently large boundary. So this is called extended system ideology. And here also we can find that total entropy generation Sgen is equal to the total entropy change, which is equal to entropy change of the system plus the entropy change of the surroundings. By assuming this is an isolated system, the surrounding and the system consisting an isolated system, we can write this equation for the total entropy generation or total entropy change. Finally, we can come up to this conclusion. There is a quantity that is called entropy generation, which is a positive value during an irreversible process, and it's going to be 0 in a reversible process. And if you have Sgen less than 0, that is an impossible process. There cannot be a process where Sgen is less than equal to 0, less than 0. So Sgen is a quantity which is greater than 0 in an irreversible process, equal to 0 in a reversible process, is less than 0. If it is less than 0, that's not no process can take place where Sgen is less than 0. That is called impossible. So if you want to check the validity of a process, you can find the entropy generation and say whether it takes place or not. So in today's in this video, we talked about the increase of entropy principle, and we found that for an irreversible process there could be a positive entropy generation inside the system other than the entropy transfer through the heat. For a reversible process, there's no entropy generation takes place. Entropy generation is 0 for a reversible process. If the entropy generation is negative, that process is impossible. With that, I'd like to conclude. See you in the next video. Thank you for watching.